Hello, Earth Science students, and welcome to your lecture number 7. This is Dr. Hurt, and I'm glad you're joining me today. We're going to be talking about, actually, it's the subject that my PhD is in. It's igneous petrology, so it's one of my favorite subjects. So it's igneous rocks. We'll be talking about igneous rocks, and this is going to build upon what you've just finished learning about, which is minerals, right? So we're going to start getting into all the rock types. We're going to talk about igneous today, and then metamorphic and sedimentary in the next lecture, and then we're going to move on from there. But we are talking about igneous rocks today, and I start off with this pretty famous picture of a bus stuck in basalt. One of my students kind of made a funny joke and said, this is Miss Frizzle's last ride, right? So it's Miss Frizzle from a Magic School Bus. So anyway, this is a bus stuck in basalt in Hawaii, and Hawaii, is a total volcanic island, and it's completely made of volcanic rocks. In this case, basalt. It's this black rock that you see before you, and that black rock is an igneous rock, right? Because it's volcanic, so it was formed from within an igneous environment. So just a little bit of review. Hopefully you remember your material from the previous lectures on matter and bonds and minerals, right? So you might recall that all rocks are formed out of minerals. They're just conglomerates of minerals. That's all it really comes down to. Just a bunch of mineral crystals stuck together. That's all a rock really is. So you have minerals, and they are made up out of atoms, and the atoms, of course, are stuck together by bonds. And the different kinds of bonds we discussed in the previous lecture 5 on matter, and those are mostly ionic bonds, right? And you remember that an ionic bond is a bond made up of two different kinds of ions. The one ion is a cation and the other is an anion. Cations are positively charged, anions are negatively charged. You should recall that ions are just a atom with a net charge. Now, a positive and a negative attract each other, right? Opposites attract. So these are held together by what are called electrostatic forces. It's the same force that will make your hair stand up if you rub a balloon on it, or make a balloon stick to a wall if you rub it on the wall. You can try either one of those at home, and you'll find that it works, right? That's an electrostatic attraction. Okay. So covalent bonding is the other kind of bonding. It's not quite as popular among minerals, but it is somewhat common. So this is, for example, the bonds that exist between the carbon atoms in diamond or graphite, right? So the more bonds that you have, the more interconnections, the more strength you have, right? And that's something that we saw with the silicate minerals. I do hope that you remember this little friend of yours called the silicate molecule, or the silicate tetrahedron. Many silicate tetrahedra together, it's called the tetrahedra when it's plural. So tetrahedron is 1, tetrahedra is 2. The silicate tetrahedra has a silicon atom right in the center with a +4 charge. It is surrounded by 4 oxygens, each one with a -2 charge. That, if you do all the math, you'll realize that this has a net charge of -4. That makes it a polyatomic anion. Okay, so it's a anion. It is indeed an anion. That means it's negatively charged, but it is made up of polyatomic. It's made up of many atoms. Okay. Now, I hope that you also remember this important review item, that your tetrahedra can link up, and it affects a lot of the properties, the physical properties of the rock and melt when those atoms link up that way. Okay, so tetrahedra that are not sharing an oxygen are called isolated tetrahedra, okay, represented by the group olivine. Some tetrahedra will link up, okay, and there were a lot of different ways in which they link up, and I hope you remember that whole part. I talked quite a bit about silicate interconnectedness and oxygen sharing, okay. So silicate tetrahedra are the building blocks of the crust. If you go outside and you pick up a rock, probably about 50% of that rock will be composed of silicate tetrahedra. So some share their oxygen atoms, some do not. Okay, some will share one, some will share two, some will share all of them. Okay, so it depends upon what the mineral is, and it all ends up determining a lot of the physical properties of that mineral. I want to review very quickly the 5 basic structures of the silicates. We have the isolated tetrahedra. Remember, those are the olivines, in which the tetrahedra are not touching. So you can see how these tetrahedra do not touch. They do not share oxygens. We have the pyroxene group, the single chain pyroxene groups, in which 2 oxygens are shared among each tetrahedra. But you'll notice that these kind of crooked chains do not touch each other. Okay. In the double chain structure, the 2 chains do touch, and you'll notice that every other silicate tetrahedra, it either is sharing 2 or sharing 3 oxygens. This guy shares 3, right? This is 3. This guy only shares 2. This guy shares 3. This guy shares 2. That is the amphibole group. This mineral right here, called hornblende, is the most common type of amphibole. You'll notice it has a real nasty formula. You do not need to memorize this formula. You'll notice, though, taking a look at the formula, it's kind of what we call a garbage can mineral. That means that it can fit a lot of different things into its structure. It could take calcium or sodium. It could take magnesium, iron, or aluminum. It could take aluminum or silicon. And it could take OH or fluoride. So it's really kind of like, it doesn't really care very much what element you throw at it, it'll take it. Okay, so that's what we mean. We call it a garbage can mineral. Okay, there are 2-dimensional sheets that are composed of every tetrahedron is sharing 3 oxygens, and it goes in this infinite sheet. This is just showing a section of the sheet. Of course, it goes in every direction in two-dimensional space, and it forms these sheet-like minerals such as muscovite and biotite, micas that are very important. You should be familiar with those, muscovite, biotite, micas. Okay, that's one of those important 6 silicate minerals. Okay, and I hope you remember that the silicate minerals are the most important mineral class in the natural world. So the last type of basic silicate structure are the framework silicates. These are the quartz and feldspars. Okay, so feldspar is the most common mineral in the crust. Quartz, on the other hand, is also very common, and it is one of the most difficult minerals to erode. It's very, very tough. Why is it so tough? It's because it has a lot of bonds. Look at how many interconnections there are. Every single tetrahedron is sharing its oxygen with another tetrahedron. So that makes it very powerful, very tough, very difficult to erode. So the silicates, there they are, right? They are the most common most common minerals on Earth, okay? The silicates are the most common class of minerals on Earth. You need to know them. You need to love them. They're going to be with you this entire class almost. So you need to know about silicates and silica, okay? Silicon is the name of the atom. Silicate is the name of the molecule, okay? Now, granite and basalt, for instance, are both common rocks on Earth, and they are both made, 50% out of silicate molecules. So these are those 6 important, just a reminder, the 6 important silicate minerals you need to know. I know this is just review, but this is just so important, you need to know it. So I'm presenting it one more time to you. Okay, you got quartz. Remember, the order is important, and you want to know it in this order. Quartz, feldspar, mica, amphibole, pyroxene, and olivine. So you want to know it in that order because that order reflects the degree of silicate interconnectedness. Olivine having totally no interconnectedness among the silicate molecules. Quartz having the most, with every single oxygen of every single tetrahedron being shared. Okay, so, and everything in between, right? Now, moving on finally to igneous rocks. Igneous rocks are, like all rocks, made of minerals. So they're just a bunch of minerals stuck together. And you can see this in the case of granite. Okay, just like the beautiful granite countertops. Some people get nice granite countertops put in their kitchens or wherever else in their bathrooms. And they love to look at them because they have these beautiful minerals in them. You can see the minerals here. The pink is potassium feldspar. The white is a plagioclase feldspar. The black little flecks are probably mica biotite, and the kind of grayish color stuff that you see here, that is the quartz. Okay, that's quartz right there. So to be a granite, you need to have 3 minerals. You have to have plagioclase feldspar, potassium feldspar, and quartz. Mica is what's called an accessory mineral. Okay, it's an accessory mineral, which means it occurs in smaller abundances, and it's not really absolutely necessary. Okay, as long as you have quartz and the 2 feldspars, you're a granite. Now, rocks are made of minerals. Okay, so here we are, feldspar and pyroxene. Now, this is a plagioclase feldspar. Plagioclase feldspar plus pyroxene is going to give you gabbro, okay, or basalt. You'll see that gabbro and basalt are compositionally and mineralogically speaking the same kind of rock. It's just that they differ in their texture. Okay, notice that this is a black rock, and it's black because it has a lot of pyroxene. Pyroxene is a black mineral. Okay. All right, so let's talk about these 3 rock types. Okay, hopefully you remember the 3 rock types from grade school. We have igneous, sedimentary, and metamorphic. We'll talk about igneous today. Now, what is an igneous rock? An igneous rock is a rock that formed from a melt. Okay, that melt can either be lava or it can be magma. There is a big difference between the two, and hopefully when you were in grade school or elementary school, whatever, high school, they impress this, your teachers impress this upon you, that there is a difference between lava and magma. They are not the same. Lava is molten rock that has erupted onto the surface. So there's your lava right there spewing out of a volcanic vent in Hawaii. But magma is all the melt you do not see. It is all the molten rock that is sitting beneath the surface in a magma chamber or in a dike or a sill. Dikes are kind of like magma chambers, except they're just, they're kind of horizontal like this, and they're usually kind of vertical or at a slant. Okay, so these would be dikes that I drew in. Sills are horizontal like this, and they're filled with magma, but they are just kind of thin. See, they're kind of like thin planes that would go like that. Those would be sills. Okay, a lot of times you have dikes connecting the sills, and they're kind of like, you can almost think of them as cracks that that are filled in with magma. Okay, so actually dikes and sills are really a lot more common than like big magma chambers like you see right here. But all of that stuff that you see, all that magma, all the dikes and sills and magma that's underground, that really accounts for a lot of the igneous rock activity, right? So it's molten rock that stays subsurface. Now, we classify igneous rocks on the basis of 2 things, texture and composition. Okay. Now, composition is what the rock is made of. Texture is it's kind of a weird term, so I'll say it kind of slowly. It's the distribution of different grain sizes, different crystal sizes in the rock. Okay. Let's take a look at some examples to make that make more sense to you. So take a look at a basalt. Now we call the basalt fine-grained. Fine-grained means that most crystals are microscopic, so you can't really see the crystals with the naked eye in a basalt. So if you just take a look at this, it looks like a pretty dull black rock. You don't see any crystals in it per se. Now there are crystals, they're just a lot of microscopic crystals. Granite, on the other hand, is a coarse-grained rock. Okay, in order to be a granite, you have to be coarse-grained, and that means that the grains have to be over 2 millimeters in size. And you'll notice that when you look at this, you can actually see the individual crystals. There's the pink potassium feldspar. There is the white plagioclase feldspar. The gray stuff is the quartz. And the black stuff there is either amphibole or mica, biotite mica. Okay, so you can actually see, and I can draw outlines around the individual crystals. Okay, that means it's coarse-grained. Fine-grained is the basalt. I can't do that with basalt. I can't pick out individual crystals. Okay, so Fine-grained versus coarse-grained, it's very important. Now, why is it so important? Why do we care about this? It's because the texture tells us everything we need to know about how that rock formed, whether it was volcanic or intrusive. That means formed in a magma chamber, okay? So extrusive rocks are volcanic rocks. So what you see right here with the lava spewing out onto the surface, this is an extrusive event, right? It's forming an extrusive rock. You can see all of the beautiful basalt building up on the surface. That's an extrusive rock, aka also known as a volcanic rock, okay? So fine-grained igneous rocks crystallize from a lava, and the reason that they're fine-grained is because when this lava got spewed onto the Earth's surface, it didn't have very long to cool. Now I want you to think back when you were in maybe middle school or elementary school. Probably a lot of you, if not everyone, did that experiment in science class where they made like rock candy. Do y'all remember that? You stuck like a stick in a supersaturated, basically a supersaturated syrup, and as the water slowly evaporated away, little bits of sugar started to build up and crystallize on your stick, okay? And eventually it comes out. You can dye it different colors, and it's cool. It looks like crystals, and you can eat it, and it's awesome, right? But how long did that take? Did that take seconds? No. Take days? No, it took longer. It took like weeks. Probably when you're a kid, it felt like months, right? Or years. It seemed like it took forever. But it took time. Same thing here with your rocks, okay? Crystals take a long time to grow. When when a lava gets extruded onto the surface like this, it gets blown out onto the surface, it's going to cool right away, and it's not going to have time to make those big, fat, beautiful crystals. On the other hand, a magma chamber is deep under the earth, and I hope that you remember from one of our first lectures that it's really hot in the earth, right? It's really hot, and it's also super insulated. That means that it doesn't lose its heat easily. You know, you have to think of the layers of rock in earth like comforters, okay? Like a big blankets. And that's what it's like. I mean, think about the fact that all of Earth's heat, not all of it, but a lot of it, is all residual heat from when Earth formed 4.6 billion years ago. And what's amazing is that that heat is still around. That intense heat is still around. I mean, that's still really hot in the Earth. Why is it so hot? Like, how does it stay so hot? It's because rock is a great insulator. It's a great insulator. It keeps the heat. And because it keeps the heat and it's hot down there, these rocks, these magma chamber rocks, are going to cool really slowly. So when you see a big granite outcrop like this, big beautiful granite outcrop, it should kind of amaze you, really. It should boggle your mind, because if you think about this, that is a magma chamber that has been brought to the surface. This used to be 10 kilometers deep, or maybe 1 or 2 or something, but it used to be really deep, maybe even 30 kilometers deep. But it's at the surface now. How did it get there? I mean, how does a magma chamber get there? It's from this combination of tectonics and erosion, so imagine you have two plates, right, coming together, and right, they collide, they start butting up against each other, and right, you can almost think of it like a train wreck, right? They start to make mountain belts as the two plates collide. And it lifts all of these rocks that maybe at one time they were pretty deep. Maybe there was a magma chamber like this, but now it got lifted up like this. And over time, what happens? If you can believe this, it's kind of amazing, but just rain, water. We're going to learn about weathering in the next couple lectures. It's going to erode that rock away, and it's going to strip it away. And over time, what's going to happen? It's going to expose that, going forward, it's It's going to expose that rock at the surface, that original magma chamber. Okay, so that's what happens. It's a process that takes millions of years, but it does happen over time, little by little. So because those rocks had a long time to crystallize, they maybe had millions of years to crystallize. Because of that, they have formed big crystals that you can see, and they're big and they're beautiful, and that's why people like granite countertops and not basalt not basalt countertops, because basalt is a boring rock that nobody wants to put in their bathroom or in their kitchen. It would just look like a plain black rock, and it's not exciting. I respect basalt, but it's not pretty to look at. So other useful textural terms. Oh, by the way, I forgot. Sorry. You should really know this. These kinds of rocks are called intrusive. That's easy to remember in a way because you just remember like inside. They form inside the earth. They're intrusive. The other term for them is pretty cool. It's plutonic. Plutonic is the opposite of volcanic. So both plutonic and volcanic are words that are rooted in Greek mythology, or actually Roman mythology. Vulcan was the Roman equivalent of Hephaestus, who was the god of fire and the god of the forge and blacksmithing. And Pluto was the god of the underworld, right? So plutonic means formed under the earth. Okay, Vulcan means it formed volcanically in this fiery extrusive event. Some other textural terms you should know: porphyritic, vesicular, glassy, and pyroclastic. You don't have to know these too much, but just want you to just have seen the terms before. Porphyritic means that you have large crystals that are in a fine-grained ground mass. So you can see that most of the rock is this black, boring, microcrystalline sort of matrix, but there are big crystals stuck in it. So it kind of looks like a plum pudding or something like that. So that's a porphyritic texture. Vesicular means it's full of bubbles. So you can see all the bubbles here, right? And glassy means that it is a volcanic glass. So that's obsidian. Okay, obsidian's a glassy textured rock. It's pretty famous because Native Americans used to make their implements and tools out of obsidian. Actually, not just Native Americans. I mean, actually, we still use in modern times for a lot of applications. We still use obsidian blades because they can actually get sharper than and by the way, Native Americans knew how to do this. They knew how to make blades that were sharper than steel blades, and still to this day, obsidian is used that way. You can actually make scalpels out of obsidian that are for surgery that are sharper than any steel that you can make, because you can make it one molecule thick blade edges. It's pretty cool. Anyway, there's a cool video, kind of shows, I'm not going to play it for you because I can never get the sound to show up very well when I'm recording this, because it's like playing from my computer and the microphone's trying to pick it up. But I really encourage you to watch it. It's a pretty cool video, and it shows a obsidian lava flow, and you'll see that it goes really slowly. It's like super thick, like, usually when you see a lava flow, it kind of looks like this, right? It's sloshy, it's flowing, it's fluid. That is kind of classic Hawaiian style lava. We're used to that. But, a lot of lava is not like that. A lot of lava is really very, very viscous. And think of, like, have you ever gone to Dairy Queen and got a blizzard? A lot of times what they do, if you get a blizzard, I don't know if they do this here, but I know, like, in Arkansas and other places I've lived, they like make it go upside down, to show you that it doesn't. It's so viscous, the milkshake's so thick, it's not going to fall out. It's not sloshy. So, most lava that erupts on the earth, or I shouldn't say most, but a lot of it is viscous like that. It's even worse. It's like a blizzard. It's like like a Dairy Queen blizzard. So it's very, very viscous. And so if you watch this video, it'll show you an example of what a lava flow looks like when it's very viscous like that. It's kind of cool. Pyroclastic rocks are rocks that are igneous rocks that have formed in a pyroclastic flow. And they're kind of cool because you might look at them and be like, wow, that looks like concrete. And it's not actually concrete. It's called a tuff. It is formed from the ash flows that come roaring down the sides after a volcanic eruption. So some volcanic eruptions we're going to learn are explosive, some are gentle. The lava style that erupts in Hawaii is actually gentle, and so it doesn't make these big explosive ash plumes, but the kind that form in maybe like Central America and South America, those are mostly very explosive, and they will create these ash plumes that are very deadly. And if you can go on YouTube, and there are like a bazillion different videos of the ash flows roaring down the sides of these mountains. There's one. There are many. This is a Mount Etna, and you can take a look at it. They're pretty cool and pretty terrifying to watch. There are some you can go on YouTube and find where like the guy's standing there and just gets like enveloped by hot ash, and I don't know what happened to him or how it got, how the footage even got there, but maybe he was live streaming it or something. But whatever, it was captured on camera. It's kind of graphic, but anyway, it's there if you want to watch it. Igneous rocks can have the same composition but different textures. So this is a good example of how that can be, right? You have basalt and you have gabbro. They are totally identical in terms of their composition. So if you sent these two rocks to a chemist and you said, what's the difference between these? And he did a bunch of chemical tests, he'd say nothing. He wouldn't be able to find, or he or she wouldn't be able to find any differences between these rocks in terms of chemistry. They're the same rock. They're only different in their texture. So if you look at the basalt, again, it's microscopic. The crystals are microscopic. You can't see them. That means they cooled quickly. That means it's an extrusive volcanic rock. The gabbro, on the other hand, you can actually see the crystals. They're not huge, but you can see them. You see that? You can see them. And that means that it is a plutonic rock. Okay, it had time to cool under the earth and make some big fat crystals. So which of these formed from a volcano? It's this guy. It's the basalt. Okay. Now, where does all this magma and lava come from? Where does it all come from? It comes from the earth, it comes from underground. But where? Does it come from the crust, or does it come from the mantle, or where does it come from? Well, most of the melting that occurs and most of the lava that is erupted is actually coming from the mantle. So how do you melt the mantle? Well, there are three ways. The three ways are as follows. So I'll take you through this. So this is a diagram of the Earth going from the surface all the way down to 6,400 kilometers at the center of the Earth in the core. Right here, this line is the CMB. I'll put CMB. That means core mantle boundary. So that's the end of the mantle right there. You'll notice that we have two different lines here. So one line, this dark blue line here, is the temperature of the Earth as you go through the Earth. Okay, you'll notice that as you get down, it moves more to the right, which is hotter. Okay, so we start off at 0 degrees Celsius, we get all the way up to 5,000 degrees Celsius in the center of the Earth, white hot. I mean, this is just unbelievably hot. Way hotter. Like you'll never probably be around anything that's 5,000 degrees Celsius. I mean, it's really way out there. Even if you're in like an iron forge, or something like that, where they're like smelting steel, you're still only talking about like maybe 2,000 degrees Celsius. So you're way down. I mean, this is like white hot, like you wouldn't believe it. Like it would actually be like, really damaging to be around the radiation coming off of this thing, because the hotter something is, the more intense the radiation coming off of it. You know that when things get hot, they start to glow and give off light, and the hotter they get, the more deadly the radiation gets as stuff comes off of it. So anyway, that's a whole different subject, but the thick bluish line here is the temperature of the Earth going through the mantle. This shaded region here, I'm going to use a different color. This shaded region is the melting temperature of the Earth on average. Okay. Now you'll notice that in the mantle, we never cross these lines, right? But they get very close to crossing right up here around maybe 100 to 150 kilometers, 200, maybe more, maybe down to 300 kilometers, okay? They get really close. So that's where most melting occurs. It occurs right in this area where the melting temperature of the Earth gets close to the actual temperature of the Earth, okay? When the mantle melts, now I want you all to remember this. So again, if you're doing something else, pay attention right now because I have a very important fact I want you to know. When the mantle melts, it produces a basalt, okay? It doesn't melt entirely. So when the mantle melts, it doesn't melt completely. It doesn't become an entire liquid. It only partially melts. So that means when it melts, only maybe like 30% of it melts. And 70% of it is left over. But 30% of it will melt, and it will produce a basalt. Okay? So, there are 3 ways to melt the mantle to produce volcanic melts, magmatic melts. You can raise the temperature. So this polygon represents where we are right now, and we want to cross the melting line. Remember that this is something we don't have a lot of intuition with, but it's true. Most materials, they don't have one melting temperature at like every pressure. Melting temperature usually depends on the pressure. Now, we're not used to that because we don't really experience a lot of different pressures. You know, we're just at like one pressure here at Earth's surface. Maybe if you scuba dive, you experience some high pressure, but unless you do that, and you're not going to be melting anything down. Well, I guess if you do like welding down at the, maybe you do have some differences there, but the bottom line is we're usually not melting things at pressure. So it's kind of hard for us to understand this, but it's true that melting temperatures increase with pressure. Okay? So the idea is, how do we get our polygon here to cross the line? So the easiest way to cross the line that we all think of is raise the temperature, okay? Make the temperature go up. So I should actually get rid of this green color and use a red color, because that's the thing we think of most, right? We just cross the line by raising the temperature. However, that's actually not a very common way to melt the mantle. The most common way to melt the mantle is by not changing the temperature, keeping the temperature the same, and sliding to the left. That means going to a lower pressure. Notice that if I keep my temperature the same and I just go to the left, I will still cross the line into the molten side. That is called decompressional or depressurization melting. Another way, which is kind of cheating, is to move the melting line. And maybe just move it so it's like this, right? That's another way of melting the mantle that is very common, and that is called flux melting. A flux is a material that lowers melting temperatures. And guess what? Water is a very powerful flux for the mantle. If any water gets down into the mantle, a lot of times causes it to melt by lowering its melting temperature. Okay? So it's the same thing. I know that we don't have too much experience with this in South Texas, but in other places, you're probably aware that you can throw rock salt on your driveway or on your sidewalk or on the streets, and it melts ice. Like if there is like a snowy day, which does happen from time to time here, but if there's a snowy, icy day, you can throw rock salt out and it'll melt the ice. Now, how do you melt ice with rock salt? Does it raise the temperature of the ice? No. Does it depressurize the ice? No. It just changes the melting temperature of the ice. Okay, it's a flux. Salt is a flux for ice. Okay, it changes the melting temperature of the ice, and that's how you melt it. So the same thing happens with the mantle, right? Water gets down into the mantle, it causes it to melt. Okay, now we have to move on to this subject to kind of better understand compositions of and how we get variations in the compositions of igneous rocks. We have to talk about this whole important series of experiments done by a guy named Norman Bowen. So Bowen was a petrologist. during the early 20th century. And the petrologist, by the way, petro means, it doesn't mean petroleum like oil. Petro means rock. Okay, it's kind of like Saint Peter, like Jesus named Saint Peter the Rock, right? Peter means rock. Like Saint Peter's real name was Simon, right? So Jesus named him a rock, Peter, Petro. I think in Spanish it's Pedro, right? So it means rock. So Bowen was a petrologist, so he studied rocks, studied igneous rocks. Now, Bowen came up with this kind of crazy experiment in which it's not crazy, it was a brilliant experiment, but it was a good experiment, but it was kind of crazy he did this. But he got a big vat, and kind of like a fake, simulation of a magma chamber, and he put a bunch of like basalt sand in there, cracked little pieces of basalt, and then he got the furnace cranking, and he melted down that basalt. And he brought it up to a really high temperature, maybe like 1500 degrees Celsius. And then he let it cool. And as it cooled, he noticed something. It didn't just cool at one temperature. And it didn't, by the way, just melt at one temperature. It melted and it cooled over a range of temperatures. And what was kind of cool is that as it cooled from initially a very high temperature, here it says 1200 degrees Celsius, it started to crystallize. But as it started to cool and crystallize, he saw a kind of interesting pattern in the kind of minerals that came out. So imagine this big hunk of magma of basalt is cooling. And the first minerals to start coming out was olivine. And then the next mineral, at the same time, pyroxene started to crystallize out. Not pyroxene, plagioclase feldspar. But it was a calcium-rich version of plagioclase feldspar. Okay, the next mineral to come out as it got cooler was pyroxene. So then the pyroxene came out. And then the amphibole came out. And then the mica came out. And then the potassium feldspar came out. And then the quartz came out. So does that order sound familiar to you? Hopefully it does, because that is what we were talking about when we were talking about interconnectivity of the different silicate minerals, right? So what's kind of cool is that order is recapitulated in the melting temperatures of these different mineral phases. So again, it's just proof that that degree of silicate interconnectedness affects a lot of the physical properties, including melting temperatures. So this is how a lot of rocks can differentiate, if you can imagine it like this. That means become different, So you can have basalt, but that initial basalt that comes from the mantle can form a lot of different rocks like granite and rhyolites and diorites and all these different things, is because it depends to what degree that basalt has cooled, right? So imagine the basalt comes up, it cools a little bit, the olivine comes out, but then that magma is still there and is able to erupt, and the stuff that erupts after that, it already lost its olivine and pyroxene perhaps, and it's going to erupt things that are like amphibole, quartz, and mica and stuff like that. Okay, so I'm just giving you kind of a model in your mind to understand how is it that we melt the mantle. From the mantle we get, a basalt, and how do we go from basalt to all the different kinds, other different kinds? How do we get differentiation? How do we get different kinds of rocks from that basalt? So I'm showing you, that's what Bowen's reaction series shows us. So we have the continuous series of crystallization on this side, which is the plagioclase feldspar crystallizing out. We go from a calcium-rich to a sodium-rich as things cool down. This is called the discontinuous series of crystallization, where we get different minerals crystallizing out. Okay. Now, you have to know, I'm going to present to you now these really important compositional terms. And these are the terms that we use to describe the composition of an igneous rock. And by the way, these are only for igneous rocks. Never use these for sedimentary rocks or for metamorphic rocks. It's a big no-no. We just don't do it. So these terms are a little weird. You probably haven't heard of these words before. They're mafic, felsic. Okay, mafic, the Ma stands for magnesium, high magnesium. The fic stands for ferric, means iron. You might know that the elemental symbol for iron is Fe. It comes from the Latin ferric term for iron. Now on the other side, felsic. Felsic, the fel means feldspar. The sic means like silicon. And these are rocks that are kind of towards this end of, so this is like kind of the felsic end of Bowen's reaction series. This is the mafic end, okay? And this is the intermediate end, okay? Intermediate part. So mafic means high in magnesium, calcium, and iron, low in silica. Felsic means high in silica, low in magnesium, calcium, and iron. These are also high in aluminum and sodium and potassium, okay? These are relatively low in sodium, aluminum, and potassium. Intermediate is just what you would think. It means intermediate, okay? Ultramafic just means supermafic. It just means even lower silicon, even higher magnesium, even higher calcium, even lower silicon, lower aluminum, lower potassium and sodium, okay? So let's take a look now at the kind of minerals we would expect from these different compositions of melt. An ultramafic rock, we draw a line like that down from ultramafic. You'll notice that it mostly goes through the pyroxene side field and the olivine field. So you can see that's mostly going to be olivine and pyroxene. Okay, that's what an ultramafic rock is like. Ultramafic rock is basically the mantle. Okay, the mantle is ultramafic. And if you go down, if we were to go down into the mantle, you might remember that I showed you pictures of what mantle rocks look like, and they are beautiful green in color, right? That green is from the beautiful peridot olivine, right? It's a gemstone, actually. It's beautiful. The other common mineral is pyroxene, okay? So that's what we see. That's what we would see in the mantle, right? The mantle is ultramafic. However, when you melt the mantle, it partially melts. That means only 30% of it melts. And the melt that comes from it when you partially melt it is mafic. It is a basaltic type of a rock. So gabbro and basalt are mafic types, okay? Gabbro is the coarse-grained, basalt is the fine-grained. Now let's take a look at what minerals you would expect in the mafic. So I'm going to draw a straight line down from here. And you'll notice that a good chunk of this is in the calcium-rich plagioclase field. So we're going to get a lot of calcium-rich plagioclase. We're going to get a lot of that black pyroxene. Or maybe we'll get little bits, perhaps, of amphibole. Maybe a little bit, right? You can see that doesn't spend much time in that field. What do we get when we get the intermediate style? Let's draw a line down from here. You'll notice we get kind of a little bit of everything. We might have a little tiny bit of potassium feldspar, which is also known as orthoclase feldspar. We will get a little bit of quartz. We will have a lot of a sodium-rich plagioclase feldspar. We might have a little muscovite, a little tiny bit of muscovite, a little bit of biotite, maybe a little bit of amphibole, maybe a lot of amphibole, right? So that's what we get intermediate. It's kind of a grab bag of different things. What are we going to get with felsic? Felsic, we're going to get a lot of orthoclase feldspar, aka potassium feldspar. We're going to get a lot of quartz, and we're going to get some sodium-rich plagioclase feldspar. Remember, I told you that to be a granite right up here, to be a granite, you have to have mostly orthoclase feldspar, that is potassium feldspar, quartz, and plagioclase feldspar. You need those three minerals to be a granite. You'll see that those are the minerals that are represented here. You might get a little muscovite, maybe a little biotite, maybe a little amphibole in there. Okay. So you need to know the kind of minerals that are going to come out and be associated with these different compositions of rock. Okay. So like on the test, if I talk about what minerals do you expect in a peridotite, you should be able to tell me olivine and pyroxene. And if I ask you what happens if you partially melt a peridotite, what's the composition of the melt that comes from a partial melt of peridotite, you should know that's going to be a basaltic mafic melt. Okay. I'm going to kind of skip this stuff because I kind of talked about this already. If you go to New York, the Hudson River Valley, Hudson River is right there next to New York City and next to Manhattan, right? There's Manhattan right there. Here's the Hudson River. On either side of the Hudson River, you get the Palisades, and these are actually really cool, very, very, very thick basalt deposits. And this used to be, if you can believe it, this used to be like a lake of basalt. And I mean, it was kilometers deep. It's mind-boggling. I mean, imagine in your mind, like one of the Great Lakes just made of lava, of basaltic lava. That's what this used to be. It's just mind-boggling, that much basalt. And what's kind of cool is we actually see Bowen's reaction series played out in that basalt. You see olivine at the bottom. You go up, you see more feldspar and pyroxene. You get up, you get more like sodium-rich feldspars as you move up, as it was cooling, because it was cooling, from basically the top up, okay, or top down, So anyway, let's talk a little bit now about mafic end members and felsic end members, because there's some very important properties of these different melts that you should be familiar with. Okay, so some of this is kind of review, but just want to hammer it home. So for mafic style lavas and melts and rocks, you have low silicon content. It's mostly pyroxene, plagioclase, feldspar, and olivine. These are the first silicates to crystallize out. They have high melting temperatures. They also have low viscosities. And that hopefully will make sense to you, because remember that these are not interconnected minerals, right? The silicate tetrahedra are not interconnected. And because they're not interconnected, it's easier for the fluid, the melt, to flow. And because it is easier for it to flow, we call that less viscous. It's low viscosity. It's more fluidic. On the other hand, the felsic style are high in silica. They're high in quartz and feldspar that are very highly interconnected. The tetrahedra are all sharing their bonds. And because of that, it's a lot harder for this guy to flow. He's highly, highly viscous. And I mean, to compare it to peanut butter, it's worse than peanut butter. It's incredibly viscous fluid. It's more viscous than, I don't know really what you can, I don't know if we have another material that you guys can think of that would be similar, but it would be like really cold, thick peanut butter. So this stuff is rich in feldspar and quartz. It's the last silicate to crystallize, has relatively low melting temperatures, and it's highly viscous. And because this is so viscous, it creates these very explosive eruptions. Okay, so imagine if I had like a water bottle, okay, like a plastic water bottle, like Arrowhead or whatever. Oh, they don't drink Arrowhead around here. I'm thinking of California. California's got Arrowhead. I don't know, what do they have, like Ozarka or something? I don't know if that, maybe I'm thinking of all these different bottled waters from different places I've lived. I don't know, I can't remember what they drink, but okay, you have a bottle of water here. Okay, and there's the water in there. And then imagine that you want to like squeeze it, okay? And you want to make the water come out. So we're gonna like drill a little hole right here, little vent. And then we're going to squeeze it. Okay? How hard is it to get that water to come out of the little hole right there? And the answer is, meh, not very hard, right? You can squeeze it and get it to come out. So that's Hawaii. Okay, Hawaii has these nice fluidic lava rivers that come out. They don't explode. They don't blow up. They're just nice and gentle. They spew out their lava and they're done. Compare that to a place like Yellowstone. Yellowstone's an amazing, amazing area. Yellowstone's in a crater. It's a crater from the last explosion, and you can stand on the rim of the crater, look down into Yellowstone, the valley below, and realize that that is a 20-mile across crater of the last super eruption that was at Yellowstone. Yellowstone's a volcanic crater. Okay, It's erupted many times, probably a dozen times. It'll erupt again someday. Why is it such a big explosion? Hawaii doesn't get blown up. Like the Hawaiian island doesn't blow up and disappear every time there's an eruption, right? It just builds up. It gets the lava, it flows out. It has to do with this viscosity. So imagine now, instead of the water bottle, instead of having water, imagine we filled it up with thick peanut butter. Thick, cold peanut butter, okay? And there's all the peanut butter in there. Okay? And then we go and we squeeze it. We squeeze it, and we want to squeeze it out of this little vent here. How well is that going to go? Well, you're going to squeeze really hard. There might be a little bit come out. You're going to have to really push hard. And if you push harder and harder and harder, probably eventually this cap is just going to blow off, and you're just going to get peanut butter everywhere, right? That's Yellowstone. So it's because that melt is so viscous, that's what causes, in part, causes the explosive eruption, explosive nature of it. Intermediate melts and intermediate rocks are just what they sound like. They're intermediate. They're between the two. So intermediate eruptions, all the big eruptions that we've had in human history have been intermediate. So Krakatoa, Mount St. Helens, Vesuvius, the volcano that destroyed Pompeii, Mount Fuji, Kilimanjaro, they're all intermediate type lavas. All of the Central American and like Mexican, Central American, South American volcanoes that are explosive, those are all intermediate types. We've never had a felsic type, Yellowstone type eruption in human history, any human history. Okay, like the last time Yellowstone erupted, there weren't humans. There were, whatever, Homo erectus or something. It wasn't like people. So we don't have. It's never happened in human history to have one of these, and these are like totally world-altering events when these things occur. So they're huge events in Earth history. So yeah, something to look forward to, I guess. But you got to know this is important stuff. So here are the 6 rock types, igneous rock types you got to know. And on the left hand side, you have the rapid cooling, fine-grained, extrusive, volcanic, aka, so you got all those things should be connected together in your mind. Rapid cooling, aka fine-grained, aka volcanic, aka extrusive rocks on the left side. Then you have the slow cooling, aka coarse-grained, aka plutonic, intrusive rocks on the right side. Okay, and to kind of like going from top to bottom, you have the felsics, and then you get down to the bottom are the mafics. Okay, so you got to know these 6 rock types. I will ask you about these 6 rock types. I will ask you on the midterm. I will ask you on the final. So you got to know these. Okay. Rhyolite is your felsic extrusive. Granite is your felsic intrusive. Andesite is your intermediate extrusive. Diorite, which is kind of like salt and pepper rock, diorite is your intrusive intermediate. Basalt is your extrusive mafic. Gabbro, your intrusive mafic rock. Notice that the mafic rocks are usually dark in color, black. The intermediate rocks are gray or salt and pepper, and the felsic rocks are pink to light in color. Okay. By the way, the average composition of the crust is andesitic or diuritic. Okay, that's the same composition, but they're intermediate. So there's just some pictures, kind of close-up pictures, just so you know what these look like. Okay, just want you to be somewhat familiar with this stuff. Basalt, gabbro, dark in color, right? Andesite, diorite are either salt and pepper, or gray. Rhyolite, granite, these are pink, salmon colored, kind of light colored. That's what you should expect. Here are igneous rocks that are named off their texture alone, like obsidian is your volcanic glass, tuff is your pyroclastic texture, right? Pumice is kind of a cool one. Pumice is basically, like when you have a really viscous, viscous fluid, It has a bunch of gases dissolved in it, like a very viscous silicate lava. Okay. It will form like a head on it when it erupts. Like, like a beer. Like you get a beer, you pour a beer. Or I don't know how old you are. Maybe you don't pour beers, but if you ever pour a beer, you get a head on it, and that head is kind of like the beer foam, So pumice is literally like rock foam. It's like melt foam. It's the foam, it's the head that formed on that lava when it extruded. So that's what pumice is. So next time you're rubbing your feet with a pumice stone, you think about that. Also, this is vesicular basalt. It's called scoria. It's that landscaping rock a lot of people put in their front yards and stuff like that, or around parking lots or whatever. It's like the volcanic rock. People call it volcanic rock. It's really a vesicular basalt. It's called scoria. All right, so that's the end of the lecture. I just want to review a couple things here. Igneous rocks are formed from melts. They can be generated by decompressional melting of the mantle, or by raising the temperature. Okay, they can also be generated by lowering the melting temperature of the mantle, but most melts are coming from the mantle. When you partially melt the mantle, remember that the mantle does not melt all the way. It doesn't melt 100%. You usually only melt it 30%. And when it melts 30%, you produce a basalt. That basalt could be produced by decompressional melting or by flux melting, or sometimes by melting by raising the temperature, although that's more rare. When those melts are formed, you form a basalt when you partially melt the mantle. However, they can differentiate and become different and form felsic melts or intermediate melts, or stay the same, be a mafic melt, based on how much the rock managed to cool before it erupted or whatever. So that's kind of related to Bowen's reaction series. Bowen's reaction series shows us that rocks don't melt at one temperature and they don't freeze at one temperature. They melt and freeze over a range of temperatures. And if the melt happens to segregate and move away after some partial crystallization has occurred, that can create a new kind of differentiate the melt. Okay. Felsic, intermediate, mafic are all terms that you should be familiar with. The felsic rocks are the granites and the rhyolites. They are high in silica, high in aluminum, high in sodium and potassium, low in magnesium, iron, and calcium. Mafic rocks are magnesium and iron rich, low in silica. They are denser, they are darker, they have more calcium. That's what the mafics are like. The mantle is ultramafic. It is a rock called peridotite. It's totally made out of a rock called peridotite. Mafic is the gabbro and basalt. That's what the seafloor is made of. Intermediate is actually the average composition of the crust, but sometimes you can differentiate the crust to form the felsic rocks such as granite and rhyolite. Remember that intrusive rocks and extrusive rocks, it's an important distinction. Intrusive rocks are slow cooling, coarse grained. That should be an A, by the way. Coarse grained. Extrusive igneous rocks are rapid cooling and fine grained, and that's because they did not have time to build those big, beautiful crystals that we know and love. So you got to know these 6 rocks: rhyolite, granite, andesite, diorite, basalt, and gabbro. You should know them by heart, and you should be able to draw this diagram out. I am going to, on the test, I may very well just give you a graph like this, and you have to tell me, like, which is the felsic fine-grained rock, which is the coarse-grained mafic rock, which is the coarse-grained intermediate rock. You need to be able to answer questions like that. Okay. Remember also regarding melt viscosities that your highly interconnected minerals such as feldspar and quartz that are high in silica are going to produce high viscosity melts, whereas the more mafic melts are going to produce things like olivine and pyroxene. Rich rocks are going to have a lower viscosity, and that all has to do with how interconnected the silicate molecules are in the melt. The more interconnected it is, the more viscous it's going to be, because it's hard to break all those bonds as the lava flows, which is necessary for it to flow and be mobile. It has to break bonds. Okay, that's the end of the lecture. I'm sorry that it's a lot of information, but such is life. So hopefully that you were able to get most of that, and please let me know if you have any questions. And I think that's all I have to say. I hope you have a good week and you enjoy the rest of your day. So this is Dr. Hurt, and I am signing out.